now we see the detailed switch implementation here. I am not going to talk about it in details, because we have already covered it earlier, where you can see how the depending on the direction of current, how the switches are conducting. So, for example, if this current is I A, which is going like this, then this transistor will be conducting and this transistor will be conducting here, and it will produce a voltage of plus VDC. Okay. So, we have seen that these operation of one H-bridge earlier in the lecture series. So, we will not go into the details, you can follow it up. Now, so we have understood that okay, fine, it is possible to cascade the output voltages of this H-bridge. So, how do we get how do we get a higher voltage waveform? This higher voltage waveform that we get is shown in this 3 cell CHB version. Okay. So, in this case you can see that this VAN is nothing but VH1 plus VH2 plus VH3, okay, sum of these 3. Now, suppose VH1, that is the voltage produced from CHB 1 or the upper CHB, is this quasi square wave like this. If VH2, the voltage produced by the second cell is this waveform, and the voltage produced by the third cell is like this waveform, and since VAN is sum, so we add these 3 waveforms and we get to this waveform, which is the total waveform VAN. If you observe this VAN waveform, we see that the peak to peak magnitude of this VAN is 3 times the peak to peak magnitude of VH1. So, it is like 3 VDC to minus 3 VDC, whereas VH1 is VDC to minus VDC. So, therefore, we see by using low voltage rated IGBTs in each cell, we are now able to produce a high voltage, okay, because the transistors or IGBTs in this each cell is rated for only VDC, okay, they are only rated for VDC like this here, okay, this is the rating for each IGBT. But now, the peak to peak magnitude of voltage that is produced at the output is considerably large than the rating of an individual device. If we have more number of cells, the peak to peak voltage in VAN will also increase further. So, this is one of the advantage of using the H-bridge, cascaded H-bridge, that by using low voltage, identical low voltage, more reliable transistor IGBTs or transistor or switches, we can get to a high voltage. Okay. Of course, we have not shown the PWM here. Okay. There is a PWM here like this, we will come to that later. There is a PWM here, 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 and so it will come here like this. We will show it later. Okay. Yes. So, this is what I was talking about, using low voltage sources, a high voltage source, high voltage can be produced at the output, where each device voltage rating is low. The one more important thing to observe is that from this waveform, for this particular waveform which I have shown, you can see that the losses are not same in each cell. in particular the conduction loss. Why? Because the first cell is only operating for this duration, the rest of the time it is 0, whereas the second cell is this and third cell is like this. So, the switches which are operating they are working for unequal duty ratios in cell 1, cell 2 and cell 3, which is evident from this waveform. And so, the losses which are incurred in each cell are different, and so we have to make some special arrangement so as to make these losses same. Okay. We will see this PWM technique, in particular level shifted PWM. Suppose we make a comparison of this CHB with a conventional 2 level voltage source converter. How do they compare with each other? So, this slide talks about that. So, suppose for a 2 level 3 phase conventional VSC, which is this one, okay, ABC here suppose. For this conventional VSC, suppose if the DC bus voltage is E, that is this voltage is E, then the voltage rating of all these devices are E, and the total number of devices we require is 6. Okay. Now, what is the peak phase AC voltage that can be produced? We have seen earlier that suppose we use sine PWM, then it is m times the DC bus divided by 2. So, the peak phase AC voltage that can be produced is for m equal to 1, that is I will say that m equal to 1 with sine PWM, is therefore, the peak voltage that you can produce is E by 2. Now, let us compare this with a 3 level 3 phase CHB. So, for a 3 level I should write here 3 phase CHB, and for also a 5 level 3 phase CHB. So, for a 3 level 3 phase CHB, if we want to produce the same AC voltage, then we need 3 isolated DC sources, each having a magnitude of E by 2. Okay. So, how does this look? This looks like this. So, this is one H-bridge, this is one H-bridge, then another H-bridge, and this is the another H-bridge. And then we connect them, and this is the A, B and C phases. Okay. So, for this is the 3 level 3 phase CHB, and then we need a DC bus voltage of E by 2. Why? Because we know that it produces 3 levels. So, it will be producing plus E by 2 0 and minus E by 2, which means that the peak voltage that it can produce, peak to peak, the magnitude is E, and it if this is same as this E here. Okay. So, if this E and that E which can be produced here are same, then the AC voltage also will be same. So, that can be produces E by 2. So, this CHB here can produce the same AC voltage of peak value of E by 2. Okay. So, the same CHB, if we are if this A B phase, the peak AC voltage that can be produced at A, B or C, if they are same all both in both cases with conventional VSC and with 3 level 3 phase CHB, then we require the DC bus magnitude E here and the DC bus magnitude of E by 2 here. Okay. But now we require 3 isolated DC bus, which is not required for the conventional VSC. But again this is the disadvantage, but there is an advantage, and the advantage is that the voltage rating of device is equal to E by 2. The voltage rating of all the devices in this is E by 2, but we require 12 devices because each H bridge has 4 devices, 4 transistors. So, we require 12, 12 devices here, whereas we require 6 devices in this converter. Okay. So, there is something we gain, something we lose. Okay. What we gain is that we get lower rated devices of magnitude E by 2, but we require more number of such devices. And of course, one major drawback is that we require 3 isolated DC sources in this converter. For this 5 level CHB, we will require 2 such H bridges connected together. We will have one H bridge, second H bridge and third H bridge, and then also another set here, and we will connect it. Like this. So, this is the 5 level 3 phase CHB. So, how many devices do we require now? We require 4 into 6, that is 24 number of devices here. But to produce the same AC voltage, now this will be now E by 4, all voltages must be E by 4. But again the major challenge is that we require 6 isolated DC source, that is a major challenge. But the advantage is we will use low voltage devices, or we can say it in a converse or in a reverse fashion, that if we use the same devices like a conventional VSC and a 5 level CHB, then we can get more AC voltage in a 5 level CHB as compared to a conventional VSC. Okay. So, these are the some pros and cons of using this converter. Now, so far we have been talking with cells having identical rating or identical DC bus. What happens if we make the voltages unequal in the 2 H bridges? For example, we can make the voltage of H1 VDC and that of H2 as 2 VDC, we can make it. So, then how will VAN voltage be? So, H1, the first cell produces 3 levels, which are VDC, 0 and minus VDC. Similarly and independently, H2 will produce 3 levels, which are 2 VDC, 0 and minus 2 VDC. From here 2 VDC, 0 and minus 2 VDC, and 0 VDC and minus VDC from here. Therefore, what is VAN? VAN is VH1 plus VH2, and for each VH1 we can go on adding. So, this plus this, say VAN is equal to VH1 plus VH2. So, you take first VH1 as VDC and then you can have VH2 as 2 VDC, you can have VH2 as 0, you can have minus 2 VDC, and this plus this is 3 VDC, this plus this is VDC, and this plus this is minus VDC. So, in this way if you go on doing, we will see that we get actually 7 levels of voltage like this, spanning from plus 3 VDC to minus 3 VDC with a 0 in between. So, 3 VDC, 2 VDC, VDC 0, minus VDC, minus 2 VDC and minus 3 VDC. So, it seems to be attractive with such asymmetrical CHB, because now we are producing more number of levels, and more number of levels, from some discussion earlier we can conclude that if the levels are more, then we will be probably going closer and closer to the ideal sine wave. So, this seems to be an attractive solution. However, the major disadvantage of having an asymmetrical CHB is that we lose the modularity, of the cells. So, for this we need, for this H1 we will need devices of voltage rating VDC, and for H2 we need devices of double the voltage rating. So, we lose the modularity, we lose the repeatability, we have to have 2 sets of cells available to us. So, this is not very attractive to the industry, okay, because they would like to go for this mass scale production. And remember that whenever we have double the voltage rating, so we need a different gate driver board. We require, so for most likely there will be the loss distribution will most likely be different, and we require a different heat sink. We probably will require a separate isolation barrier between the bus parts, because the voltage ratings are different. So, several changes in the design has to be made when this we use two types of cells. And also if you have if you want to have a fault tolerant feature, where you want to, suppose one of the cells has been damaged and you want to quickly replace that cell, then you must have two types of cells spare. For example, in this case we must have two types of devices as spare, one with VDC rating and one with 2 VDC rating. So, losing the modularity and using different voltage rating devices is not very attractive. And so, although we get some advantage of having this asymmetrical CHB, but it has not been success commercially. And so, we will not discuss this in further, and we will stick to the CHB with equal ratings for further discussion.